All right, so let's see. Your programming test 1 result, I will check with the TA, but it seems like they are definitely on a good track. So by the end of tomorrow, for sure, I'll give that to you. Hopefully early tomorrow. Yeah, not very likely to be today, since I'll finish my class rather late today. So I'll touch base with the TA to make sure they can give me all the necessary things, and then I can do a final processing on the stuff. I should be able to release the result tomorrow, for sure. Hopefully not too late tomorrow. And for your lab number 3, okay, it has been released. I know you got very busy preparing for your written test number 2, but lab number 3 is also very relevant to the final programming test that you're going to have also later, right? Not very distant future, but so you definitely want to also get started with that. I'll show to you about what you should really pay attention to. So if you go to the E-class, and there you will see lab number 3 instruction over there. Right? Notice that for this lab over here, I divided that into 2 parts. So part number 1 is something that's very familiar format that you have been doing for your lab number 2, the practice test, the practice programming test, and the actual programming test. Just about given some problem description, create some machine. But in this case, it's not even machine, just the context. And then, so that'll be part 1. It's going to be informally due. You don't need to submit anything, but you should really get it done before next Wednesday. You got about a week, right? Try to really prepare that at the same time as your written test 2. It's going to be worth your time. And then next Wednesday, we're going to release the second part, which is about how you can interact with the rodent prover. The rodent prover itself is a very complicated tool. To really master that in general is not feasible, even for the entire course. So what we decided to do is to really talk about a very particular pattern that you have to follow. So we got step-by-step guidance that's going to be updated next Wednesday. You just got to follow through, make sure you follow every step and the logic behind. So that'll be the plan, okay? And then submission deadline will be a week after. So you'll be Wednesday, March 29th. All right, and then your programming test is about 1 week later. So you do have some time to really get things prepared. I'll try to give you some example question, for programming test 2 later. But it's absolutely critical for you to just make sure you complete each part in time. All right, so you can look at the problem itself. It's quite an interesting one, not very sophisticated, but it does show for theorem proving approach, you can actually even model hardware components. For those of you who maybe study about digital circuits, these are something you're very familiar with. Of course, we are doing something very simple just to show you the idea. And people in the industry or in the research community, they actually try to formulate their hardware implementation, which could be several thousands of gates that can be composed together. And they try to prove some nice properties about it. And we'll do just some very basic one, so you get a feel. Right, so that's the general problem. You should really read it through, make sure you know what's going on. And you will be given something very similar in the actual programming test 2. And part 1 over here, just follow through the instruction, create a project, create a context, and then etc. Several axioms over here and 1 theorem for you to think about how to formulate them. I didn't give you too many hints over here at this point based on the English description and also the problem description, especially this diagram over here. Take very, very close look at this diagram over here to see how things can be specified and versus being implemented. If you got any confusion about this, you should really reach out to me and we can clarify further. All right, so that's about part 1. And then you will see that 2 out of the 5 proof obligation will get automatically discharged. Doesn't seem to be acceptable, right? So what we're going to do is we're going to do in part 2, show to you for this axiom over here, for these 2 theorems, how can we actually prove them manually by interacting with the prover. Quite a bit of mouse clicks, but it can easily get lost. So that's why rather than giving you some tutorial video, we have step-by-step written instructions. So you can really follow through and take notes at the same time. All right, that's something I would like you guys to learn next week. All right. Anyway, so this will be updated. As soon as it's updated, I'll let you know. And then you can definitely continue to the second part. Before that, just pay the foundation for part 1. All right, guys, any general confusion about lab number 3? We good? Okay. And have fun. I think it's an interesting lab. Challenging, but I think it's worth your time. Completely some challenge, so you will learn something. All right, so that's about lab 3. And then we do have some example questions for you for your written test number 2. And would you guys find useful to have another review session about the written test too? Okay, maybe Q&A? Okay, so I will get in touch with you guys. Since your test is on Thursday, in the worst case, we can do like a Wednesday evening, like last time. So how about I touch base with you again, maybe next Tuesday, right? Okay. Definitely, I'll give you guys some review session if that might help. Definitely, by all means. Okay, there will be a review session, and to be confirmed. Okay, and guys, don't forget, even though your written test number 2 and programming test 2, they are not going to cover the makeup lecture, which is an FTP case study. But make sure you study that steadily. I'm pretty sure there will be some question on the exam about it. So you definitely want to study that, right? Don't try to cram everything the day before the exam. Not very healthy, okay? Alrighty, that's everything I think I want to remind you. Otherwise, I think we should really dive into bridge controller again, okay? So what did we talk about last time? Last time, basically, we just talked about something called guard strengthening. And the diagram that you want to keep in mind, I will just remind you very quickly, is this diagram like over here. If you have two models, one is more abstract than the other one, which is more concrete. And we have some refinement relationship between them. Of course, the concrete model refines the abstract model. And then for any events that already exist in the abstract model, somehow you're overriding it in the concrete model. And one rule is to say the guard over here called abstract guard and the guard over here called the concrete guard. There should be some implication relationship that should be satisfied over there. I spoke about the intuition behind this implication. You guys can review and let me know if you got further confusion. But always remember, guard strengthening tells you the guard at the concrete world should be stronger, okay? Cannot be weaker, okay? That's basically what we talk about. And then we talk about how you can formulate the proof obligation for guard strengthening. You want to do that for every events that actually exist, both in the abstract and the concrete. And we got two events. And today, possibly after the short break, we're going to talk about what about those events that only exist in the concrete model. They don't really exist in the abstract model. It turns out there's an interesting event called skip that we have to devise to really help us do some proof obligation. But we'll get there, maybe after the break. Okay, and then we talk about proof obligation and the proofs, right? That's what we did last time. And hopefully, if you haven't got a chance to do this proof, it will be a very nice exercise and useful exercise for you to get ready for next Thursday, the test. Okay, and I think when you actually go through the example question, I think that will give you quite a bit of idea about what might be on the actual test. The level of difficulty could be a little bit higher, but I think the format will be very similar, especially given two sequence over here, let's say. Right, I'll say these two sequence, does there exist a sequence of inference rule between them to complete a proof? That would be a very typical question I'd like to ask in the written test. Yeah?
So you have the two sequences. So the first one is what we start with, and the second one is what we end with.
Yes, correct. Yeah, of course, convention is we always go from left to right, of course. Yes. I wouldn't suddenly just switch the order to say go from right to left. No, I wouldn't do that. Right? Always left to right. Okay. Yeah, guys, just excuse me for today. I'm having a little bit runny nose, kind of allergic to the weather. Bear with me. All right, so let's now continue. And what we like to do now is to talk about invariant preservation. Right? For MLL and MLN, how can we do invariant preservation? The plan will be, we'll try to show to you the proof obligation rule to tell you what's new really over here. And then we try to formulate the proof obligation as a sequence together, and then the proof themselves will be left as exercise for you. Okay, so we can do a little bit of proof after the break, okay, in a different proof obligation. But don't worry, solutions are also on the slides. You can always compare. Okay, for invariant preservation, right? So invariant preservation, we actually talk about it when we talk about M0. So there should be no surprise, not too much. Right? There will be some minor thing you have to watch out for, which I'll show to you. All right, so this is the proof obligation rule. Okay, let's take a look at that more closely. Okay, let's take a look. Okay, we talk about invariant preservation. And one thing you also want to remind yourself, when we talk about invariant preservation over here, we talk about the old events, which exist in both M0 and N1. And we're going to switch the context a little bit after the break. We're going to talk about two events that only exist in N1, but not M0. But for now, we're still talking about two events you are very familiar with. So we got ML out over here. Also, we got ML in over here. And we proved earlier that ML out, ML in, they preserve the invariant for the abstract model. Similarly, we want to prove that ML out also preserve all the invariants in the concrete model. And ML in also preserve all the invariants in this model. Right? It's very logical over here. And let's look at the rule very quickly. Okay? So here we have, number one, the axiom that you have to put. And the axiom are not really shown over here, but the axiom are actually shared by M0 and M1. We'll look them up a little bit later. And then over here we have, this is the abstract invariance. You can see over here we're only referring to V. And if you recall, V simply means all the variables in the M0, the abstract model, which is N. And all the invariants will be, this will be the abstract invariance. Okay, over here is simply I. And the next one will be something called concrete invariance. Concrete invariance. And here you can see we got both the V and also W. And W, again, that's the formal component we went over last time. That one is the concrete variables. And you can think about these guys over here are the J that we are referring to over there. Over here, right? That's a J. And let's now try to look at something also very important. Guys, what is this? If you remember. H. Yes. That's a guard, but is it a guard at the abstract world or the concrete world? Concrete, okay? The way to tell it, I'm pretty sure that's how you judge, is you can see W over here, right? Good, so let's say if we talk about ML out, so this will be the H. And if we talk about ML in, this would be the H. Okay? Depending on which event we are talking about. And finally, you can see this J over here. Notice that this J and this J, they are the same J, except that when you want to prove the invariant as a goal, you prove one by one. But when you put invariant as hypothesis, you put all of them. Okay? You put all the concrete invariants as hypothesis. However, when you want to discharge them, you discharge them as goal one by one. So that's why it's indexed. Okay? So in our case, you can think about the I. The I over here tells you it's going to go from 1 to 5. You can see 1, 2, 3, 4, 5. All right? Okay, so in the concrete invariants, they might refer to the constant, and also somehow we have to worry about the effects of the abstract world and the concrete world. Okay? You can definitely look up to see what it means for the E and F. But I'm going to show to you exactly how you can manipulate it. Okay, one more annotation, and then let's now formulate the proof, the sequence. So this will be the concrete guard. All right, before that, why don't we answer this question very quickly? How many sequences should be generated based on this rule? 2? Which 2? I agree, one for ML out, but one for ML in. Yes. However, don't forget, J here is indexed. And J here can either be 1 or 2 all the way to 5. You have to discharge them separately. So 2 sequence is actually not right. Instead, the 4, it should be more. Yeah. Why 10? Yeah, exactly. That should be fine. Yeah, that should be 10. All right, guys, be careful. You should really know. It's not really, I don't necessarily ask you to generate all the sequence, in the exam, but you should really know at least how many there are. I might just want you to generate some of them, okay? So the answer is, for this question here, we actually got 10, which is 2 multiplied by 5. And the 2 over here is the ML out and also ML in. Right, the 2 old events that actually exist in both the concrete and the abstract world. And the 5 over here is the 5 invariants in M1. Okay. Let's show you 2 of them. Okay, and the 2 of them, we also got some invariant preservation proof, which is also, I'm going to leave them as exercises for you. But let's now at least know how to formulate them, which is a very important first step. Yes?
Are we choosing to do the ML invariance for the sequence because we're doing the model for ML?
Yes, exactly. So we are because we're not talking about the refinement number 1, M1. And we already proved M0 is correct, based on the different criteria a few weeks ago. Yeah. So now what we want to do is to also prove M1 being correct. And now we're moving towards that. The only thing we have proved so far about M1 is about the concrete guard being strengthened from the abstract guard. That's the only thing we have proved. Now we are trying to prove more. Okay? Let's now try. Okay, I'm going to write down the name. Okay, there are 2 things I want to do. The first one here, let's say we do ML out. And then, let's say we want to preserve invariant number 4. Invariant 1, 4. Okay, this one here. And then we talk about invariance preservation. Okay? So this is the first one. And the second one there will be, let's say, ML in. And for this, for a different invariant, let's say invariant 5. Okay? ML in, and then invariance 1, 5, and then for invariant preservation. Okay, so these are the 2. Okay? Now, why don't you guys just take 1 minute? If you got a piece of paper, why don't you try just 1? Okay, I'm going to do that after 1 minute. For example, for this one here, what should be the corresponding sequence with lots of hypotheses over here, according to here, and then there will be something that we want to prove as a goal. And in order to derive this part here, you have to use the before-after predicates of the corresponding action for the events. All right, why don't you try for just 1 minute to see what you can get. That's definitely something you will want to know how to do as well for the test. Now give it a try, and then we'll put it down in a minute. Now just make sure this is ML out, ML out. And we got ML in, ML in. And also invariant 4, invariant 4. Invariant 5, invariant 5. Ryan, question? Yeah, so, sorry, say it again. I don't quite see the question. Yeah, so Ji over here simply tells you I here is a particular invariance. So you can see the invariance. So the indices we have, that's what I here we instantiated by into. About I being 1, so that means we talk about preserving this particular invariance. We don't really try to prove all the invariants being preserved in a single sequence. That might be way too complicated. So that's why we decompose them into several. Mm-hmm. Yes. Absolutely. So think about, okay, thinking this way. So think that this one here, yes. Yes, let me write it down, exactly. So this one here is the effects of the events, let's say E, in the abstract states. And this one over here will be the, okay, this is not a very good color. F over here will be the effects. And I'll give you one example right away of the same events. E in the concrete states. For example, if we look at ML out, E here is n plus 1. F here is a plus 1. Okay, that's kind of the substitution we have to do. I'm going to show that to you. Similarly, if we look at MLN, the E here is n minus 1. And the F over here is the C minus 1. But not necessarily every invariance is going to involve both the abstract and concrete variables, only some. So here, this is actually just to say in general, you may have to use both, but not necessarily every time. Okay? All right, guys, just in case you have some answer to compare, let's see. This is what you will get. Okay? Let's now start with the axiom. And the axiom, sorry about that, I don't really have the fragment over here, but you can look it up from the previous page. The axiom will just be D is a natural number, and D larger than 0. Okay, I'll put down the number here. Axiom 0, 1, and also axiom 0, 2. All right, and then we have the abstract invariance. Right, so what I just have done was the axiom. What about abstract invariance? For the abstract invariance, it's going to be these two. Okay, so I'll put n a natural number, and also n less than or equal to d. Right, so this will be invariance 0, 1, invariance 0, 2. Okay, next one, it's pretty standard, like a routine. The next one will be the concrete invariance. We want to put every one of them. Okay, be patient, let's now do it. So now we say A should be a natural number, B should be a natural number, and also C should be a natural number. And then A plus B plus C equals N, A equals 0, or C equals 0. All right? So these are the concrete invariants, right? Okay, for now, just for spacing, I wouldn't put the names for the labels. All right, so this is really important because between these two sequences, they are going to share the same context over here. Okay, so let's now do a little bit copy and paste. So let me just make this guy here a little bit smaller, so I will be able to accommodate. Okay, this is 1 over here. Okay, and the same guy is going to be shared for the other proof sequence here too. So far, I'm done with just these 3. Now, what about H? Depends on which event you're talking about. Since we are now talking about ML out, so the concrete guard should be this one here. So I'm going to put A plus B less than D, and also C equals 0. ML out guards. All right, the concrete guards. And for the right side, we have C larger than 0, right? C larger than 0. So this is the guard of ML in. All right, we're almost there, but for this part here, there's going to be a single go over here. I'll put a star. Also, turnstile, there will be another one. I'm going to do them separately. Okay, star, star. To figure this out, I would say this may be the little bit trickier part to figure out. You just got to do some of the proper substitution. But at least make sure you're following so far, right, to formulate a sequence. Okay, so now, for this one here, let me say the star over here. Okay, I'll put star here. Since we are talking about invariant number 4, which is over here, And if you recall, for the very first time we talked about invariant preservation, we are basically saying the invariance at the post states should remain holding, right, in the post states. So the intermediate manipulation could be something like this. Since invariant number 4 is actually this one here. So what I will do is A plus B plus C equals N. But since it's going to hold at the post states, I'm going to prime all the variables. This is what you should start with. But this is not the final answer just yet. But it will help a lot if you start with this. Okay? And then this is where I just responded to Ryan earlier. This is where the E and F could be useful. These are the effects, like before-after predicates. So now what should we replace A prime by? We have to refer to the before-after predicate for ML out, right? Remember the before-after predicates for ML out. Let's write it down. A prime equals A plus 1. B prime equals B. C prime equals C, right? Let's now do the substitution. A prime is A plus 1. B prime is simply B. C prime is simply C, right? And then, so that's basically the F part, right, the concrete one. What about E, right? Here, what will be M prime? Then you have to look at the corresponding action over here for ML out. And that one there should be M prime equals M plus 1. So you're going to replace this one here by M plus 1. Let's now simplify that. So that means you got something like A plus B plus C simply equals N. Still the same. But that's okay, right? That's something you want to calculate first by doing the substitution. Okay? Okay, can you see how to simplify that? You know, A plus B plus C and then plus 1 cancel out. And that's what you will get. But if you like, I think it might be, if you do something like this. You can say A plus 1 plus B plus C equals M plus 1. Without simplification, it's actually okay. But that might be a little bit more explicit about we have considered the before-after predicate for both the abstract and the concrete actions. Yes? Yes, so just have to you have to remember when we say turnstile and then we'll talk about invariant preservation. What we really want to prove as a goal is to say that invariance actually holds at the post states after the event transition. So that's why I try to prime all the variables to begin with. That talks about the invariant itself holding in the post states. And then we have to replace every prime over here by the corresponding before-after predicates over here. That's what we did. Good. Guys, are we okay? Yep. Adnan. Yes. Not necessarily. So just in this case, happen to be the same. Just happen to be. Yes. So Adnan's question was, are we always going to get just the same invariance? It would be nice, wouldn't it? In that case, there's no point of doing replacement. Not necessarily. Just happen to be the case. Yeah. All right. For this one here, you will see I have some for you. Okay. This proof sequence is something we just derived. And guys, this will be some exercise for you. Okay. Again, being nice to you, I told you already here will be the inference rule you will need. You may just want to practice by out to see if you can find out which ones are relevant for the inference rule. Yes?
Can we simplify the goal to
Yeah, absolutely.
N1?
Yeah, for this one, if you want to simplify, that's absolutely fine. That's fine. That one is completely up to you. Yes. All right, why don't we do this one here very quickly, just for completeness, right? I want to make sure you guys everybody's okay, just about this one here. All right, I'm going to put star over here. Okay, this guy here. Okay, what should that be? And this one here is about invariant number 5 over here. Okay, so we have A equals 0 or C equals 0. And talking about invariant preservation, so this should be the post-state evaluation for the invariant. That should be true. So let's prime everything. You don't prime constant, so 0 remains 0. Okay? And then what should we do as a substitution? A and C, right? You can see here we have no abstract variable. So we don't have to worry about n minus 1 for MLN. We don't have to. Okay? So the only thing we have to worry about is over here, C minus 1, right? And of course, the before-after predicates, let's write it down. C prime equals C minus 1, A prime equals A, and B prime equals B. Okay? A prime equals A. C prime equals C minus 1. And add it in. That's the question, answer to your question. You can see now they are different, right? But I like that question. All right, so this is actually the final answer. You don't need to simplify. You just say A equals 0 or C minus 1 equals 0. Okay? So this will be the second exercise you will see over here. And this one turns out to be a little bit more complicated. You can see I even give you a rule, ORL. Okay? That one there is going to split the sequence on the halfway through into 2 independent branches. That's really something you will have to make sure you understand. All right? All right, these 2 exercises. Okay. Guys, are we okay? Good. Invariant preservation is actually not too bad. You just have to know how to do the substitution. Sometimes you may have to go both the abstract version and the concrete version for the before-after predicate. That's the only new bits. Yes?
How come in LLM we didn't equate the goal to n minus 1 out with the before-after predicate, just like how we did in LLM?
Yeah, we don't need to because if you look at this particular invariance, okay, here we're talking about invariant number 5, right? Which is over here. And this is the invariant that only involve A and C, the concrete variables. If only the concrete variables are involved, you only have to worry about concrete action. There are certain invariants that's kind of a bit special. They involve both the abstract variable and the concrete variable. In that case, of course, you have to also go back to the abstract version to do the transition. It depends on what's really needed.
So basically it all depends on finite substitution.
Yeah, it depends on the nature of the invariance. If the invariant involves both the abstract and concrete variables, of course, you got to consider before-after predicate for both the abstract version and the concrete version. On the other hand, if the invariant only involves concrete variables, then you only consider the concrete action. Yes, yes. Yeah, that's actually very important to notice. Okay. All right, so guys, you can see this kind of stuff. What you have to remember is the principle. But depending on what the specific example you might be given, you have to know how to derive the proof obligation. That's the tricky bit. So that's why you got to practice, right? And you know what? You can practice even more, I can tell you. Remember we said before how many there are? 10. We only got 2. How many are missing? 8. For your sake, you may want to see systematically what are the other 8. At least, I think you should really figure out the names of the other 8 proof obligation, at least, based on this naming convention. And then maybe choose some of them, and then put a common part, and then to put the corresponding invariance over here. Okay, that's what I would suggest. It's also an exercise that's set in the slides. Okay, good. Yeah, the exercise is over here on the at the bottom. Yeah, prove the other 8. So here 8 is a magic number because it's 10 in total. We only got 2, so we got another 8. Okay, so one more observation, like a recap, and then we can take attendance and take a short break, and then we can talk about other things. Okay, one more. Okay, finally I can stop sweating. So hot in the beginning. Okay. All right, so this diagram here, sorry, it's on the iPad, but I'm going to show it to you. This diagram. All right. This diagram is actually from the textbook, but it's a very standard diagram about understanding the abstract events and the concrete events, how they are supposed to be related together. We did see something like this last time. Okay, let me remind you. Okay, the only difference is when I did it last time, I tried to make some concrete example to show to you. But this one here is the more general version. Okay, let me show to you the diagram, and then I need to use this diagram to do one more observation, and then we'll take a short break. Let me show to you where you should really look at. So if you, oh, there we go, right? Think about this guy over here, right? The 1, 2, 3, 4, fourth state over here is really like an instantiation of the 1, 2, 3, 4 in the diagram, right? Okay, if you already understood what I exemplified last time, this one here is not too bad. Okay, let's now take a look at this more general diagram. Okay, let's take a look and try to understand it. Okay, let me just go to this diagram here, and then let's see what we can say about it. There we go, over here. Let's see, understand about these two parts, right? I want you to pay attention to this direction here and this direction over here. Okay, these two first. So this one here is at the abstract model. And this part is about making a decision at a concrete model. Okay? So think about this one over here is about a state transition in the concrete model. And for example, it could be M1. Okay. Let me just be even more explicit. For example, the M out in M1. All right, so that's the concrete transition. And this one over here is the corresponding transition in the abstract model. The corresponding state transition in the abstract model. And for example, it could be the same events, right, since we talk about M out, but it will be in M0. Okay, let's understand how we move from one to another. Okay, so we are saying that whenever you're doing some transition at a concrete state, at the concrete state space, there's always some corresponding one. So that's how you relate the two models together to say one is the refinement of the other. It's a very important diagram to show to you. And now, we ought to understand about two things. One is, this part here is the pre-states of the transition, right? I'll write it down. Think about this is the pre-states of the abstract transition. And this state over here is also the pre-states, but is the pre-state of the concrete transition. Okay, so of course you're going to notice they're both pre-states. But one is about concrete, the other one is abstract. Abstract here, and concrete over here. And even more we can say about the pre-states. The fact that this abstract event can take place suggests that the event's guard, in this case G, must be true. Otherwise, it's not enabled, right? So that's why you see the G over here. So the G here is, so this will be true, means the abstract events is enabled. Okay? And then we got another one over here, which is H. That's a concrete guard. Right? Also, we talked about abstract guard versus concrete guard, right? A lot. This would be true, means the concrete events is enabled. If one event is enabled but not the other one, we cannot see the correspondence. Right? And remember what we said last time about guard strengthening. Now you can see why it's actually necessary. If I have my concrete events enabled over here, in order to claim that this is the corresponding abstract events, its guard must be enabled as well. Right? Otherwise, it wouldn't make sense. So that means H should imply G. That's the guard strengthening that we talk about, right? So this is the last point I would like to make about the pre-states. And think about the G and H over here. So you have to remember guard strengthening, which means H should imply G. Okay, we can try to put things together. All right, so that's about the pre-state, which is a little bit more tricky to understand. But once we say, okay, so the pre-state, both of them, both states enable the corresponding abstract and concrete events so they can take place. Okay? How about these two states themselves? They're also being related by the concrete invariants. Okay? For this one here, let me just point to you once more, okay, if I may. If you go back to this diagram over here, you can see we got we got abstract states, we got concrete states. And the invariant that's going to relate them together is this special invariance, which involves both the abstract and concrete variables. Okay? Just remember. Okay, let me put it down. And then we'll talk about post-state very quickly. I owe you guys a break very soon. Okay, this one here will be the invariance relating the two pre-states. All right. Okay, final bits. Let's say we are able to make a transition for the concrete world. And this is to say the post states, right? You want to really understand the notation here. So you can see W prime is equal to this, right? Let me write it down here. When we say W prime is equal to F, C, and W, right? W prime over here is the post states because we got prime of concrete variables. Okay? If you remember, something like when we got A prime and C prime, right? Like that. Okay? And then this part over here, this will be the effects of the concrete transition. Okay, similarly, if you look at this one here, V prime over here, this will be the post states, right? Let me just write it down for completeness of abstract variables. Okay, and over here, this will be the effects of abstract transition. This is simply saying, if I try to make a transition, let's say MLN, MLN, the post state for the abstract world should be N minus 1. The post state for the concrete world should be C minus 1. Okay, that's what it is saying. Final point. How are these two states related? Again, by the same invariance. But now you want to notice that. Okay? The V here and the V prime over here versus the W here and the W prime over here. You can see that the same invariant J holds in the pre-states. Also, it holds again at the post-states. All right? That's the final point. And I'll write it down. The same linking invariance holds at the post states. Yeah, so don't be too scared by this diagram here when you look at that. It's a very neat way to really summarize what's going on. And there's also some very standard term of calling such diagrams. It's called commuting diagram. commuting. Okay, which means I can go from here to here. That's one way to think of it. Or I can say, I can simply translate from here to here first and make an abstract transition. And then from here, I can also relate the two. Yeah, like a commuting diagram. You can get to the same destination by two different routes. That one's a little bit aside. Yes?
It seems to me why every abstract transition should seem to have a concrete state. Other way around would be true. Like, say you had let's say a rule that, let's say you had a rule that whenever a car got onto the bridge, another car must also go.
Yeah.
From
So.
from why would that state? From B to C. Why would that state transition have to be simulated?
Yeah, you want to think about the flow that we are following here. Number one, so since we are now trying to do some refinement, so that's the model we are concerned about at the moment, right? So we want to make sure every possible transition we can make in the refinement model, which is a concrete model, and we are not really creating any new behavior. So what we're doing here in the concrete world, there is some corresponding one that can be simulated in the abstract world. That's what we're doing. You don't do the other way around. Not really. You want to make sure everything we do in the concrete, in the refinement model, there's a corresponding one in the abstract.
Oh, okay.
Okay? Okay, good. If that makes sense, but we can talk about it again in case new confusion comes out. Guys, long waiting break, right? Let's take attendance, but make sure you review this. I would say for your written test number 2, let's cover only up to here. Okay? I think that's enough. All right? There will be a little bit about invariant establishment. I wouldn't worry too much about it. That's okay, just here. Okay? And to be more precise, it's going to be until slide 60. Okay, also easier to remember. Okay, slide 60. Okay? That means you got to study from slide number 2 to slide 60 for your written test 2. All right? Okay. In case I forgot to really remind you guys, but you want to remember. Okay? Okay, so let's now take attendance, and let's definitely take a short break. Otherwise, too much draining for you, for your brain. Okay, let's now start a class. And then let's do the poll. There we go. Yeah, checking please. Huh?
It doesn't ask for multiple choice.
Oh, it doesn't? Oh, really? It should, right? There we go. Yeah. All right, everybody's good? All right. I'll stop it and then take a 2 minutes break and then we'll come back. Okay. Question? Yes. Yes, yes.
So as soon as you get tau on one side, it's okay to just discharge it the whole thing using arithmetic, right? So like
you mean if you got this one already, right?
Yeah. So like if false implies P.
That's correct. But actually, that's very good because at some point, we're going to talk about one more inference rule. That one there tells you if the hypothesis happen to be false. In that case, it's an axiom.
Oh, okay.
It's yeah.
Okay.
But that's good, yeah.
And also for this side, I got to here, and then I just stated that because of these two rules, I just use arithmetic to make them both true. And then if one side is true on the OR, then you could just discharge
Okay.
this arithmetic.
That makes sense to you? Yep, yep.
Okay.
That's fine.
Okay.
Good. Question?
I mixed the attendance.
You missed the attendance? Okay. Can you find your name here? It's sorted by last name. That's you?
Yeah.
Okay, can you please put the check mark and then sign? Very good. Thank you. Hi, Sarah. Hi. Yes, of course.
For this, you know how you said there's like 8 more that we need to prove?
Yes, yes.
So like for this, would like one of them be like ML out invariant like 5?
Invariant 1, 5, and then ML, and then invariant. Yes, that's
like
correct.
That. Oh, okay.
Exactly. There'll be 8 more.
Okay, yeah. And I also am wondering, can I come to your office like a bit earlier?
A little bit earlier today?
Yeah.
Yes, that's possible. Do you think 15 minutes might be okay?
Yeah, whatever works for you.
How about 3:15?
Yeah, yeah.
Yeah, in case the door is locked, just knock, and then,
Okay.
yeah.
Thank you so much.
Okay, no problem. All right, guys, 1 more minute, and then we'll resume. Okay, we'll start in just 1 moment. All right, guys, let's resume, please. Okay. Yep, so you know what? My apologies. Before the break, I said it should be slide 60, right? You may not actually want to be only stop at 60 because I forgot. Starting from 61 is actually a solution to the proof. So you may want to look at that too, right? So I shouldn't say 60. Again, my apologies. It should be until, okay, this will be the first proof. Okay, take a look. That'll be the second proof. Okay, this will be a little bit more complicated. And then I would say 64, not 60. Okay. Yeah, other than that, I have one suggestion. So next Tuesday, we still have a class. And I would suggest next Tuesday, I'm going to spend a class to finish off the first refinements. Okay. We just need to talk about the new events and something called life lock or divergence. There will be some tricky proof obligation that we have to get right. If time permitted, I also talk about something called relative deadlock freedom. But I'll rather maybe start you fresh, maybe next Tuesday. So how about we call it a day? Would that be okay? Unless you got any objection. It doesn't happen often in my class, don't worry. But that's, I would say today, I think that's good. Why don't you guys think about how you may want to plan for studying for your written test number 2. I think it's definitely important for you to consider what we have talked about today, how to figure out the proof sequence. Okay, today I feel comfortable. I can let you go earlier. Next Tuesday, come and then I will start you fresh about new events. All right, thank you. I'll see you next time.